There is a galaxy falling toward you right now. Not metaphorically, not in some abstract, cosmic sense. At this very moment, as you lie here, as the weight of the day settles and the room grows dark and quiet, a galaxy containing 400 billion stars, a structure so vast that light itself takes 100,000 years just to cross from one edge to the other, is moving through space in your direction. It has been moving in your direction for a very long time, and one day, in a future so remote that the word future almost loses its meaning, it will arrive. The galaxy is called Andromeda. You may have seen it. On a clear night, far from city lights, it appears as a faint smudge, barely visible to the naked eye, a soft blur hanging just off the constellation Cassiopeia. It looks fragile. It looks still. It looks like something that has always been there and will always remain there, fixed and quiet in the deep dark above you. But it is not still. Andromeda is the largest galaxy in our local group, the small family of galaxies to which the Milky Way belongs. It spans approximately 220,000 light-years across. It contains somewhere between 800 billion and 1 trillion stars, more than twice the number in our own galaxy. It has at least 2 large satellite galaxies of its own, Messier 32 and Messier 110, and a retinue of smaller dwarf galaxies in tow. At its centre sits a supermassive black hole weighing in at approximately 110 million solar masses. And it is heading directly for us. Right now, Andromeda is approximately 2.537 million light-years away. That is the distance that light travelling at 299,792 kilometers per second takes 2.537 million years to cross. It is, by any human standard, an incomprehensible distance. The entire recorded history of human civilization, every empire, every invention, every war, every language ever spoken, spans less than 10,000 years. Andromeda is so far away that even in the time it took our species to walk upright, invent fire, build the pyramids, write the first poem, and land on the moon, light from that galaxy has only closed a tiny fraction of the gap between us. And yet, it is coming. The velocity at which Andromeda is approaching us has been measured with extraordinary precision, using data from the Hubble Space Telescope, and later refined with observations from the European Space Agency's Gaia satellite. Then astronomers have calculated that Andromeda is moving toward the Milky Way at approximately 110 kilometers per second. That is roughly 396,000 kilometers per hour. That is faster than any spacecraft ever launched by humanity. The Voyager 1 probe, the fastest object our civilization has ever sent into space, moves at approximately 61,000 kilometers per hour. Andromeda is moving toward us at more than 6 times that speed. At 110 kilometers per second, closing a distance of 2.537 million light-years, the arrival will take approximately 4.5 billion years. 4.5 billion years. That number is worth sitting with for a moment because it is not small, even by cosmic standards. 4.5 billion years ago, the Earth did not exist. The Sun did not exist. The solar system as we know it, every planet, every moon, every asteroid, every comet, had not yet formed. The substance of your body, the iron in your blood and the calcium in your bones, was still scattered across interstellar space, drifting in the aftermath of older stars that had lived and died long before our sun ignited. 4.5 billion years is, roughly, the entire age of the Earth. The collision, if we can call it that, will happen in a span of time equal to the entire lifetime of our planet to date. That is the clock. That is the countdown, and it has already started. Let us begin at the beginning. Let us begin with the question that, once asked, makes everything else fall into place. How do we know Andromeda is coming? The answer starts with light and a technique called spectroscopy. When astronomers look at a distant galaxy, they are not just observing brightness or shape, they are examining the spectrum of its light, the distribution of wavelengths emitted by the billions of stars within it. Every element in the universe emits and absorbs light at very specific wavelengths. Hydrogen, helium, calcium, iron, each has a kind of fingerprint, a unique pattern of bright and dark lines in the spectrum. These fingerprints are universal. They are the same across the entire observable universe. But when a light source is moving toward you, those fingerprints shift. The wavelengths compress. The light becomes slightly bluer than it would be from a stationary source. This is the Doppler effect applied to light, the same physics that makes a passing ambulance's siren rise in pitch as it approaches and fall as it recedes. When the light shifts toward the blue end of the spectrum, the source is approaching. When it shifts toward the red end, the source is moving away. Most galaxies in the universe show a redshift. They are receding, carried away by the expansion of space itself, the ongoing consequence of the Big Bang. The universe is growing and most of its contents are drifting apart. Andromeda shows a blue shift. When astronomers measure the spectrum of Andromeda's light, it is shifted unmistakably toward shorter wavelengths. Andromeda is not retreating. It is not holding still. It is approaching. It is one of the very few large-scale objects in the observable universe that is actually getting closer to us rather than farther away. The expansion of the universe is not sufficient to overcome the gravitational attraction between the Milky Way and Andromeda. Gravity has already won. The two galaxies are falling toward each other, locked in a mutual gravitational embrace that has been tightening for billions of years. This was first understood in the early 20th century. Vesto Slipher, an American astronomer working at Lowell Observatory in Arizona, measured the radial velocities of various nebulae, the objects we now understand to be galaxies, in the 1910s. He noted that the Andromeda Nebula, as it was then called, showed a distinctly blue-shifted spectrum, moving toward the Milky Way at what he estimated to be around 300 kilometers per second. His measurements were rough by modern standards, but his conclusion was correct in its essence. The refinement came later. Edwin Hubble in the 1920s established that Andromeda was indeed a separate galaxy, not a nearby cloud of gas within the Milky Way, but an entire island universe at a staggering distance. And subsequent decades of observation, culminating in the precision measurements made possible by the Hubble Space Telescope and the Gaia satellite, have pinned down the approach velocity with remarkable accuracy. In 2012, a team of astronomers led by Roland van der Marel published a landmark study in the Astrophysical Journal that provided what remains the most detailed analysis of the impending collision. Using Hubble measurements of the sideways motion of stars in Andromeda, a painstaking effort requiring multiple years of observations to detect the incredibly small angular shift of stars 2.5 million light-years away, they were able to determine not just how fast Andromeda was approaching, but in which direction it was actually heading. This was a crucial distinction. For decades, key astronomers had known that Andromeda was getting closer, but they did not know whether it was heading directly at the Milky Way's centre, or whether it would pass by at some angle, a near miss rather than a direct hit. The sideways velocity of Andromeda determines which of these scenarios is true. Van der Marel's team found that Andromeda's sideways velocity, its motion across our line of sight, as opposed to directly toward us, is relatively small. Small enough that the collision, while not perfectly head-on, is direct enough to count as a genuine merger, rather than a glancing blow. Andromeda is not going to miss us. Now, when we say collision, we need to be very careful about what we mean. And this is where the story becomes strange in a way that takes some time to fully absorb. Galaxies are not solid objects, or they are not like two balls of rock slamming into each other. A galaxy is mostly empty space. In fact, the word mostly does not begin to capture the emptiness of a galaxy. A galaxy is almost entirely nothing. Consider our Sun. It is, by any human standard, enormous, a sphere of plasma approximately 1.4 million kilometers in diameter. The nearest star to the Sun, Proxima Centauri, is approximately 4.24 light-years away, roughly 40 trillion kilometers. That distance is about 30 million times the diameter of the Sun itself. If you imagined the Sun shrunk down to the size of a basketball, Proxima Centauri, and on the same scale, would be another basketball, sitting approximately 8,600 kilometers away. The two basketballs would be separated by a distance roughly equal to the diameter of the Earth. The Milky Way contains somewhere between 200 and 400 billion stars, each separated from its neighbours by similarly vast distances. When Andromeda's 800 billion stars pass through this volume of space, the odds of any individual star from Andromeda directly colliding with any individual star in the Milky Way are, for practical purposes, negligible. The stars are so spread out, so separated by void, that the two galaxies will mostly pass through each other like two ghosts walking through the same wall. There will be no great chain of stellar explosions, no cascading collisions, no apocalyptic fireball of suns, and yet the collision will be, in every meaningful sense, catastrophic. Because what makes a galaxy is not just the stars. It is the gravitational architecture that holds those stars together. It is the dark matter halo, the invisible scaffold of mass that surrounds and permeates the galaxy, providing most of its gravitational force. It is the precise orbital dynamics of hundreds of billions of stars, each one moving in a path set by the collective gravitational pull of everything around it. It is the interstellar gas and dust, the raw material of star formation, distributed in vast clouds throughout the galactic disk. When Andromeda arrives, all of this architecture will be disrupted. The gravitational interaction between two galaxies of this size is not a gentle thing. As they approach and eventually intersect, tidal forces, the same kind of forces that raise ocean tides on Earth, but scaled up by incomprehensible factors, will stretch and distort both galaxies. Stars will be flung out of their orbits. Some will be ejected entirely, be cast out into the intergalactic void on trajectories from which they will never return. Vast streams of stars will be drawn out into long, arcing tidal tails, rivers of suns stretching hundreds of thousands of light-years into space. The interstellar gas clouds will be compressed by the gravitational disturbances, triggering violent episodes of star formation. New stars will be born by the billions in the chaos, and eventually, after multiple passes and over the course of several billion years, the two galactic cores will sink toward each other and merge into a single new galaxy. That new galaxy does not yet have a name in any official register, but the astronomers who have studied this event most closely have taken to calling it Milkomeda, or sometimes Milkdromeda. It will be neither spiral nor barred spiral. It will be an elliptical galaxy, a vast, smooth, featureless cloud of stars with no distinct disk, no elegant spiral arms, no great lanes of star-forming gas. It will be the kind of galaxy that looks quiet because it has already spent its youth in fire. But we are getting ahead of ourselves because before the collision, there is the approach. And the approach has its own timeline, its own phases, its own escalating series of events, each one separated from the last by hundreds of millions of years. Let us walk through it. We are currently, in the language of this countdown, approximately 4.5 billion years from first significant contact. The galaxies are still cleanly separated. From Earth, Andromeda is a faint smudge just barely visible. The nearest stars of Andromeda are more than 2 million light-years away, and no meaningful gravitational interaction between the two galaxies has yet begun. Or rather, the interaction that does exist is what has already been driving the galaxies toward each other across cosmic time. The long-range gravitational pull that set this whole story in motion billions of years ago. But even now, the two galaxies are not entirely unaware of each other. The Milky Way and Andromeda are already gravitationally bound to each other, part of the same local group, a collection of more than 50 galaxies, most of them small dwarfs, that are all gravitationally associated and will eventually, over the next several trillion years, all merge into a single object. The gravitational influence between the Milky Way and Andromeda currently manifests primarily as the approach itself, the acceleration that has been gradually increasing the closing velocity between the two galaxies over billions of years. There is also the matter of their satellite galaxies. Both the Milky Way and Andromeda travel with retinues of smaller companions. The Milky Way has the large and small Magellanic Clouds, two irregularly shaped dwarf galaxies visible to the naked eye from the southern hemisphere, each one a brilliant smear of light across the night sky. Andromeda has its own satellites, including the dwarf elliptical galaxies Messier 32 and Messier 110. There are also dozens of smaller dwarf galaxies associated with each of the two major galaxies. These satellite galaxies will be affected by the collision long before the main event. As Andromeda approaches, its gravitational influence will distort the orbits of the Milky Way's satellites and vice versa. Some of the smallest, most loosely bound satellite galaxies may be stripped away entirely by the approaching tidal forces. The Magellanic Clouds have a particularly interesting destiny. Current models suggest that the large Magellanic Cloud may actually collide with the Milky Way in its own separate event, perhaps 2 billion years from now, well before the Andromeda collision. This smaller collision would itself be a significant event, potentially disturbing the structure of the Milky Way's disk, triggering some star formation and possibly disrupting the orbits of stars in the outer regions of the galaxy. By the time Andromeda arrives, the Milky Way will already have absorbed one of its largest satellite companions. But let us focus on the main countdown. In approximately 2 billion years, roughly the halfway point to first contact, Andromeda will have closed approximately half the current distance between the galaxies. At that point, it will be perhaps 1.3 million light-years away. The closing velocity will have increased due to gravitational acceleration, moving from the current 110 kilometers per second towards something higher. Models suggest the galaxies will be approaching at several hundred kilometers per second by the time they actually reach each other. From Earth, if the Earth still exists, if anything resembling human civilization still persists, which is by no means guaranteed by any scientific model, the night sky in 2 billion years will look noticeably different. Andromeda, currently a faint patch of light approximately 6 times the apparent width of the full moon, though far dimmer, will have grown larger in the sky. It will still be too faint to see during daylight, but on dark nights it will be clearly visible, larger, more extended, beginning to show more of its internal structure. The Sun will also be changing on this timescale. Our Sun is a middle-aged star currently about 4.6 billion years old and estimated to live approximately 10 billion years in its current hydrogen-fusing phase. As it ages, over the next billion years, it will very slowly brighten. In approximately 1 to 1.5 billion years, its solar luminosity will have increased to the point where Earth's oceans begin to evaporate, the water cycle breaks down, and the surface becomes uninhabitable for complex life as we understand it. This is a separate countdown entirely, one running in parallel to the Andromeda clock, and one that will, in most models, expire before the Andromeda collision begins. The fate of life on Earth, if there is any, is not primarily determined by the galaxy falling toward us. It is determined by the star at the center of our solar system growing too bright for the world we live on. The galaxy collision is what happens afterward. It is what happens to our solar system, wherever it ends up, in the deep future, long after Earth as a living world is gone. Approximately 3.75 billion years from now, something changes. This is the phase astronomers call the early perturbation period. Andromeda has closed to within perhaps 800,000 light-years. The gravitational interaction between the two galaxies has grown strong enough to begin producing measurable distortions in both structures. The outer halos of both galaxies, the extended, diffuse regions of dark matter, and loosely bound stars that surround each galactic disk have begun to overlap and interact. At this stage, the galaxies themselves are not yet visually interacting. They are still distinct objects, but the gravitational field is already working. Tidal forces are beginning to stretch the outer edges of both galaxies. Stars in the periphery of the Milky Way feel a noticeable pull in the direction of Andromeda. Some of those stars begin to deviate from their regular orbits in the night sky. Andromeda now spans a significant fraction of the visible sky. It is not just a smudge anymore, it is a galaxy. You can see its disk. You can see the bulge at its center. On dark nights, the spiral arms are faintly visible. The sky in this era would feel crowded with it. Andromeda has grown into something vast and present, a permanent fixture of the night, like a second Milky Way rising at a different angle. It is around this time that both galaxies would begin producing the first of their tidal distortions. Tidal tails, long streams of stars drawn out by gravitational interaction, start to form at the edges of both systems. These tails are not visible to the naked eye at first, being composed of relatively sparse stellar populations, but they are real structural changes. Both galaxies are beginning to fray at the edges. More the interstellar gas clouds in the outer regions of both galaxies are also being disturbed. Gas that had been sitting quietly in stable orbits for billions of years is being nudged, compressed in some places, and rarefied in others. This is the beginning of what will become in later phases a burst of star formation unlike anything the galaxies have experienced since their own formation billions of years ago. But the great drama is still 500 million years away. At approximately 4 billion years from now, Andromeda is close enough that the two galaxies are in what models describe as the regime of strong tidal interaction. The closing velocity has increased significantly. Andromeda's disk, seen from Earth's solar system, wherever in the galaxy that solar system might be by this point, fills a substantial portion of the sky. Next, we should pause here and acknowledge something important. The models that describe the Andromeda collision, including the landmark 2012 Van der Marel study and subsequent simulations, are probabilistic. They give us trajectories and timelines that represent the best current understanding, but there are uncertainties at every level. The precise sideways velocity of Andromeda, the distribution of dark matter in both galaxies, the initial positions of individual stars, all of these introduce uncertainty into the simulation. The broad strokes of the collision are well-established science. The fine details are still being refined. What the models agree on is this. Within approximately 4 to 4.5 billion years, the outer disks of the Milky Way and Andromeda will begin to physically overlap. During the first pass, the moment when the two galactic disks actually interpenetrate is the defining event of the collision, and it happens approximately 4.5 billion years from now, give or take a few 100 million years. That is the deadline. That is the moment this whole video is counting down to, and as we approach it over the next several billion years, the night sky above any inhabited world in either galaxy will undergo a transformation unlike anything that world's inhabitants have ever seen. A galaxy will rise in the sky, not a faint smudge, not a distant blur, a full-scale spiral galaxy, alive with light, growing larger with every millennium, sweeping across the heavens in a slow, inexorable approach that spans the entire history of human civilization many times over, arriving in the sky with a grandeur that no mind, however vast, could fully prepare itself for. There is one more thing worth understanding before we move forward in the countdown, the question of where our solar system will end up. The Sun is currently located roughly 26,000 light-years from the center of the Milky Way, about halfway between the galactic center and the outer edge of the disk. It orbits the galactic center once every approximately 225 to 250 million years. Over the 4.5 billion years remaining before first contact, the Sun will complete somewhere between 18 and 20 additional orbits of the galactic center. During the collision, the Sun's orbit will be perturbed. Gravitational interactions with stars from Andromeda and with the distorted gravitational field of the merging galaxies could alter the Sun's trajectory significantly. It could be flung inward toward the dense central region. It could be flung outward toward the periphery. It could, in extreme scenarios, be ejected entirely from the merging system into intergalactic space. Current models estimate a roughly 12% chance that the Sun will end up in a very different part of the final merged galaxy than it currently occupies, flung to the outer halo or even partially ejected. The most likely outcome, however, is that the Sun remains somewhere within the main body of the merged galaxy, though in a significantly different orbital position than it currently holds. The solar system itself will almost certainly survive the collision intact. The distances between stars are so vast that the probability of another star coming close enough to actually disrupt the orbital mechanics of our solar system, close enough to disturb planetary orbits, fling planets away, or cause direct stellar interaction, is extremely low, but not zero. In any given pass, most solar systems will experience nothing more dramatic than a change in their galactic address. It is the sky that will change, the view, the context. Lying beneath that future sky in a solar system that has drifted to some new position in the chaotic remnant of two colliding galaxies, any life that still exists would look up and see something extraordinary. They would see the universe rearranging itself. They would see, written in fire and starlight across the entire dome of the sky, the story of what happens when two of the largest structures in our cosmic neighborhood finally run out of room between them. They would see the deadline arrive. Imagine standing outside on the clearest night you have ever seen. No city lights, no moon, just you and the full weight of the sky pressing down, the Milky Way arching overhead like a river of cold fire, and somewhere off to one side, a faint smear of light that is not a star, not a cloud, but an entire galaxy. 2.5 million light-years away, ancient light arriving at your eyes after a journey that began before our ancestors walked upright. That smear is Andromeda. That is what it looks like right now. Now imagine that same sky, but 4 billion years from now, the smear is gone. In its place, filling perhaps a quarter of the entire visible sky, is a structure of breathtaking complexity, a tilted spiral disk of light, the bright core burning like a second sun without heat, spiral arms trailing off into the darkness in long, sweeping curves, each arm speckled with the blue-white fire of young stars and the rust-red glow of ancient ones, not a smudge, not a blur, a galaxy, hanging directly overhead, enormous and silent, growing imperceptibly larger with every million years that passes. This is the sky that greets the beginning of first contact, not at the moment of collision. That is still 500 million years away from the scene we are entering now, but at the moment when the two galaxies stop being distant objects and start being each other's context. When the gravitational conversation between them shifts from background murmur to something that is actively reshaping both structures. When the first physical consequences of the approaching merger become real, measurable, and visible. When the clock stops counting down in billions and starts counting down in hundreds of millions. To understand what happens during first contact, we need to understand tidal forces. Not ocean tides, though the physics is identical, but galactic tides. Forces operating at a scale so vast that the word force feels inadequate. Tidal forces arise from a difference in gravitational pull across an extended object. The moon exerts a gravitational pull on the Earth, and that pull is stronger on the side of the Earth facing the moon and weaker on the far side. This difference, this gradient in gravitational strength, stretches the Earth very slightly along the Earth-Moon axis and compresses it perpendicular to that axis. The oceans, being fluid, respond to this stretching by bulging outward on both sides. That is the tide. Now apply this principle to a galaxy. A galaxy is an extended object, a disk of hundreds of billions of stars spanning tens of thousands of light years. When another massive galaxy approaches, its gravitational pull is stronger on the near side of the first galaxy and weaker on the far side. The result is a tidal force that stretches the galaxy along the axis pointing toward the approaching galaxy, and, as conservation of momentum demands, compresses it somewhat perpendicular to that axis. But unlike the solid rock of the Earth, which resists this tidal stretching and only deforms by tiny amounts, a galaxy is not rigid. Its stars are held together only by gravity, orbiting in paths that are already the result of a delicate gravitational balance. When you add a strong tidal force to this system, the balance breaks. Stars that were on the outer edges of the galaxy, the most loosely bound, most vulnerable to perturbation, begin to deviate from their original orbits. Some are pulled toward the approaching galaxy. Some are flung in the opposite direction, and some are drawn out along the tidal axis into long, curving streams of stars, structures astronomers call tidal tails. Tidal tails are the first visible signature of a galaxy merger. They are, in a sense, the galaxy coming apart at its edges. Long rivers of stars, sometimes containing millions or even billions of individual suns drawn out of the main galactic body and trailing behind the collision like the wake of a boat. They can extend for hundreds of thousands of light years. They can persist for billions of years after the main collision is complete. We can see them right now in other galaxy pairs. Look at the antennae galaxies, NGC 4038 and NGC 4039, a pair of interacting galaxies approximately 45 million light-years away in the constellation Corvus. They are currently in the early stages of a merger. In photographs, their most striking feature is not their cores, but their tails. Two enormous sweeping arms of stars extending away from the main bodies of both galaxies, curving gracefully into space like the antennae of an insect. Those tails are made of billions of stars, stripped from the outer disks of both galaxies by the tidal forces of the collision. The Milky Way and Andromeda will produce their own tidal tails, both of them. The Milky Way's outer disk will begin to develop tidal distortions, and long streams of stars, drawn out by Andromeda's gravity, will arc away from the main body of the galaxy into the intergalactic medium. Andromeda will develop the same structures, two great tails, one from each galaxy, sweeping out into the void. Current simulations of the Milky Way-Andromeda collision, particularly the high-resolution N-bodies simulations run by teams, including van der Marel's group, and subsequent work done with increasingly powerful computing resources, show these tidal features developing clearly in the final few hundred million years before first contact and growing dramatically during and after the first pass. The timeline of first contact runs roughly from 3.5 to 4.5 billion years from now. At 3.5 billion years out, the separation between the galaxies has closed to somewhere around 600,000 to 700,000 light years. The dark matter halos of both galaxies, which extend far beyond the visible stellar disks, reaching out for hundreds of thousands of light years in all directions, have already begun to overlap significantly. Dark matter halos are not sharp-edged structures. They are diffuse, gradually thinning as you move away from the galactic center, but they extend remarkably far. By this stage in the approach, the outer dark matter halos of the Milky Way and Andromeda are already interpenetrating, passing through each other, beginning the gravitational handshake that will ultimately fuse the two systems. This overlap of dark matter halos is, in a sense, the true beginning of the merger. The dark matter is where most of the mass is. Roughly 85% of the total mass of a galaxy is in its dark matter halo, not its stars. When the halos begin to merge, the gravitational architecture of both galaxies begins to change. Orbits that were set billions of years ago and had been stable for all that time start to feel new gravitational influences. On the stellar disks, the visible parts of both galaxies are still separated at this point, still distinct, but they are no longer operating in isolation. The gravitational field each disk inhabits is no longer the smooth, symmetric field of a single undisturbed galaxy. It is a distorted, asymmetric field shaped by the approach of an enormous external mass. Stars in the outer disk of the Milky Way, in the region beyond, say, 40,000 light-years from the galactic center. begin to respond. Their orbits develop slight eccentricities they did not have before. The disk begins to warp in the same way that a spinning top wobbles when an external force acts on it. The outer edges of the Milky Way begin to curve upward on one side and downward on the other, like a vinyl record left in the sun. This warping is not hypothetical. The Milky Way's disk is already slightly warped right now, a feature astronomers have known about for decades and have attributed in part to the gravitational influence of the Magellanic Clouds and the larger-scale environment of the local group. What will happen in 3.5 billion years is the same effect, amplified by orders of magnitude. At 4 billion years from now, the halfway point between our current era and first contact, the approach enters what we might call the visible perturbation phase. The separation has closed to perhaps 400,000 to 500,000 light years. From the solar system, wherever it happens to be at this point in its galactic orbit somewhere within the Milky Way's disk, the view of Andromeda is no longer the faint smudge of our era. Andromeda now covers an angular area of the sky many times larger than the full moon. Its disk is clearly extended, tilted at an angle relative to our line of sight. The central bulge glows with the combined light of billions of tightly packed old stars, a warm yellowish-white luminosity concentrated in the core. The spiral arms, less bright than the core but unmistakably present, trail outward, studded with the blue-white fire of young star clusters and threaded with dark lanes of dust. On dark nights, the tidal tail of Andromeda, the first of the great stellar streams being drawn out of its outer disk, may already be faintly visible as a long, faint extension arcing away from the main body of the galaxy. The night sky in this era is genuinely different from the one we know. It is busier, more complex. There is more to look at. And for any civilization that exists to witness it, and we should acknowledge that on a 4 billion year timescale, the likelihood of any biological life resembling us having survived is essentially zero, though the universe is endlessly creative. The sky would have the quality of something that is visibly, unmistakably in motion. Not in the way that planets and stars appear to move across the course of a night, but in the way that over the course of generations, over the course of what such a civilization might call its geological history, the sky itself would be changing. Andromeda would grow, slowly but measurably. In the records of any civilization patient enough to keep them, Andromeda would grow. The star formation story begins in earnest during this phase, and it deserves its own careful attention. Both the Milky Way and Andromeda contain enormous reservoirs of interstellar gas, hydrogen and helium, with traces of heavier elements, distributed in clouds throughout the galactic disk. This gas is the raw material of star formation. Under ordinary conditions, a gas cloud must reach a critical density before it collapses under its own gravity and ignites into a star. In both galaxies, star formation has been proceeding at a moderate rate for billions of years, a few solar masses of new stars per year in the Milky Way, somewhat more in Andromeda. But conditions are about to become far from ordinary. As the galaxies approach, the gravitational disturbances from the tidal interaction compress many of the gas clouds. Compression increases density. Increased density triggers collapse. The result is a dramatic increase in the rate of star formation, what astronomers call a starburst. This starburst begins modestly during the approach phase in the outer regions most affected by the early tidal forces, but it will become far more intense during and after the first pass. Current simulations suggest that the collision of the Milky Way and Andromeda will trigger one of the largest bursts of star formation that either galaxy has experienced since its own formation in the early universe, a period billions of years ago when these galaxies were young and full of the raw gas needed to build new suns. This has a double consequence that is worth dwelling on. First, the starburst creates enormous numbers of new stars very rapidly. Many of these stars will be massive, far more massive than the Sun. Massive stars live fast and die young. A star 10 times the mass of the Sun burns through its hydrogen fuel in perhaps 20 million years, a tiny fraction of a Sun-like star's 10 billion-year lifespan. When massive stars die, they do so dramatically. They explode as supernovae, releasing in seconds more energy than the Sun will emit over its entire lifetime. During the starburst triggered by the Andromeda collision, supernovae will be going off throughout both galaxies at a dramatically elevated rate. The sky, any viewpoint within the merged system will be threaded with the light of exploding stars. Some supernovae will be bright enough, if close enough to any inhabited world, to be visible in daylight. Second, the supernovae from these massive, short-lived stars seed the interstellar medium with heavy elements, carbon, oxygen, and silicon, iron, and dozens of others, synthesized in the nuclear furnace of the dying star and blasted outward into the surrounding gas. These heavy elements are the building blocks of planets, of chemistry, of life. The starburst triggered by the Andromeda collision will, in a very real sense, enrich the interstellar medium of the merged galaxy, seeding future generations of star systems with the materials needed for worlds like Earth. Out of destruction, the raw ingredients for creation. Now, let us turn specifically to what happens in the solar system's immediate environment during first contact. Here is the essential thing to understand. The Sun and its planets will almost certainly not be directly involved in any stellar collision. And the stars of Andromeda and the Milky Way will pass through each other largely without hitting individual suns. The probability of any specific star from Andromeda colliding with, or even coming within, say, a light year of our Sun during the first pass is extremely small. But almost certainly and extremely small probability are not zero. Current estimates suggest that over the course of the entire merger, which will unfold over several billion years and involve multiple passes, the probability of another star coming within 1 light year of the Sun is perhaps a few percent. Not negligible, but not likely either. The solar system has survived for 4.6 billion years without a stellar close encounter. The odds during the merger are better than those of a direct hit, but they are not zero. What matters more than direct encounter is the gravitational perturbation of the outer solar system. The Sun's gravitational influence extends far beyond the visible planets. The outermost edge of the solar system, the Oort cloud, a vast spherical shell of icy bodies that surrounds the solar system at distances between 2,000 and 100,000 astronomical units from the Sun, is only loosely bound. Gravitational influences from passing stars or from the changing galactic tidal environment can nudge Oort cloud objects inward, sending them on long inward trajectories that sometimes bring them through the inner solar system as comets. During the galactic merger, the gravitational environment of the solar system's neighborhood will change significantly. The density of stars in the vicinity of the Sun may increase, depending on where exactly the Sun ends up in the merging system, and passing stars will be more frequent. This increased stellar traffic will perturb the Oort cloud more frequently, potentially increasing the rate at which comets are sent inward toward the inner solar system. It will not be an apocalypse. The inner solar system, the rocky planets, if any still exist in some form, will not suddenly be bombarded with thousands of comets. The perturbation will be statistical, gradual, perhaps a modest increase in the rate of comet deliveries, a somewhat higher background rate of impacts, nothing catastrophic in any individual century, but cumulatively, over millions of years, a different pattern of bombardment than the solar system experiences today. There is another phenomenon that deserves attention during this phase, the behavior of the supermassive black holes at the centers of both galaxies. At the center of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of approximately 4 million solar masses. At the center of Andromeda sits a black hole that is substantially larger, approximately 110 million solar masses, roughly 27 times more massive than our own galactic center's black hole. During first contact, these two black holes are still billions of light-years apart within their respective galactic cores. They will not interact directly for a very long time. But as the galactic merger unfolds over billions of years, the two cores, each carrying their central black hole, will spiral toward each other through the merged galactic body, and gradually losing energy to dynamical friction, the drag force exerted on a massive object moving through a field of stars. The eventual fate of these two black holes is one of the most dramatic endpoints of the entire merger story, and we will return to it in later parts. But during first contact, what matters is that the increased star formation and gas inflow triggered by the merger may cause both black holes to become more active. When a supermassive black hole has a supply of gas falling into it, it does not just absorb that gas silently, it heats it. The gas forms an accretion disk, a swirling, superheated disk of material around the black hole, and as it spirals inward, it releases enormous amounts of energy as radiation. A sufficiently active supermassive black hole, fed by infalling gas, just becomes an active galactic nucleus, a source of radiation that can outshine the entire rest of the galaxy. During the merger, gas will be disturbed and funneled toward both galactic centers. There is a real possibility that, during the most intense phases of the collision, one or both of the central black holes could become briefly active. Not bright enough to pose any danger to stars or planets at ordinary distances, but spectacular enough to be visible as a bright point source at the center of the merging galaxy, visible from any vantage point within the system. The Milky Way's own galactic center may, for the first time in billions of years, briefly glow. We should also look at what the full night sky looks like from the solar system during this phase, not just Andromeda, but the entire visible universe. As seen from a point somewhere within the Milky Way during early first contact. In our current era, the night sky contains roughly 6,000 stars visible to the naked eye. The Milky Way arches overhead as a broad band of diffuse light. A handful of other galaxies are faintly visible, Andromeda to the north, the Magellanic Clouds from the southern hemisphere, perhaps Messier 33 in Triangulum if conditions are perfect. In the first contact era, the sky is transformed. Andromeda dominates. Depending on the exact geometry, the approaching galaxy might span anywhere from 30 to 60 degrees of the sky, a structure so enormous that no single human-scale field of view could contain it. The Milky Band of our own galaxy still arches overhead, but now it competes with this second vast structure, tilted at a different angle. It's crossing the Milky Way at some point in the sky where the two bands of light intersect. Depending on the orientation of the Milky Way's disk, Relative to Andromeda's disk, this could create a sky where two rivers of galaxy light cross each other, an X-shaped double band of stars and glowing gas arching from horizon to horizon. A sky unlike anything Earth has seen in its 4.5 billion years of existence. The tidal tails are visible as well, long, faint streams of stars, drawn out of both galaxies by the gravitational forces of the encounter, trace arcs across portions of the sky, dimmer than the main galactic bodies but unmistakably present on the darkest nights. These streams are not just abstract structures, they are actual stars, millions of individual suns, but displaced from their original home in the galactic disk and now tracing new trajectories through the interstellar medium. The star count in the night sky increases. As the star density in the solar system's vicinity rises, due to stars from Andromeda beginning to intermingle with Milky Way stars in the outer regions of both disks, the number of naked-eye stars increases modestly, not dramatically. The solar system is still likely to be in a relatively uncrowded region, but the sky grows slightly brighter. More stars, more structure, more evidence in every direction of the transformation underway. At approximately 4.5 billion years from now, the most dramatic single moment of the entire merger timeline occurs. The leading edges of the two galactic disks make first physical contact. This is not a sharp event. So there is no particular moment when someone could point to a clock and say, now. But within a span of perhaps 50 to 100 million years, fast, by galactic standards, the outermost regions of both stellar disks are occupying the same volume of space for the first time. Stars from Andromeda are now genuinely neighbours of stars from the Milky Way in the outer regions of both disks. Two galactic populations, each ancient, each evolved in relative isolation for billions of years, now share the same local universe. The gravitational interaction at this moment is intense. This is the phase where the tidal tails fully develop, drawn out rapidly as the gravitational forces on the outer disk stars spike dramatically when the approach is closest. Gas clouds in both galaxies are being compressed and disrupted simultaneously. The starburst escalates sharply. Across both galactic disks, particularly in the regions where they are actively overlapping, massive stars are forming and dying at spectacular rates. Supernovae are going off at elevated frequency. The cores of both galaxies, the dense central bulges containing the oldest stars and the central black holes, are still separated. The first pass does not bring the cores together. It is a pass, not a direct collision of the dense centers. The two cores will fly past each other, still separated by tens of thousands of light years before the galaxies continue through each other, slow down due to gravitational drag, and eventually fall back for a second pass. Picture the moment. A solar system, perhaps our solar system, perhaps another, somewhere in the outer disk of what was once a clean, spiral galaxy. The sun still shines. Whatever worlds orbit it are still turning, and in the sky everything has changed. Looking in one direction, the bright core of the Milky Way, still there, still glowing, now more active than it has been in billions of years, a warm, concentrated light at the center of a still visible disk structure. Looking in another direction, Andromeda's core, now enormously bright in the sky, not a smudge, not a blur, but a galaxy core, a concentrated blaze of ancient stars rivaling the Milky Way's center in apparent brightness, the entire Andromeda disk spreading outward from it across tens of degrees of sky, and everywhere, in every direction, at every angle, the remnants of the tidal interaction, streams of stars arcing between the two galaxies, regions of intense blue-white light where new stars are forming in compressed gas clouds, dark lanes of dust backlit by the starburst below, the whole sky transformed into a tableau of galactic collision happening slowly enough that no individual lifetime could perceive its motion, but unmistakably there, the signature of two giants in the process of becoming one. This is what first contact looks like. Not a bang, not an explosion, not an apocalypse, a rearrangement, a slow, ancient gravitational rearrangement of everything: stars, gas, dark matter, orbital paths, night skies, running on a time scale that dwarfs all of human history the way an ocean dwarfs a raindrop. And it is just beginning. The cores are still intact. The black holes are still billions of light years apart within their respective structures. Yet the first pass is underway, but the pass will complete, and the galaxies will separate slightly and then fall back together for a second approach. The collision proper, the core passage, the starburst peak, the chaotic scrambling of billions of stellar orbits is what comes next. There is a moment in every collision, whether it is two cars on a highway, two raindrops on a window pane, or two galaxies in the dark between the stars, when the outcome becomes inevitable. Before that moment, there is still, in some theoretical sense, a way out, a different trajectory, a different velocity, a different angle of approach that would have sent one object sliding past the other into the void. The encounter a near miss rather than a merger, the aftermath a brief disturbance rather than a fundamental transformation. After that moment, or there is no way out, the moment for the Milky Way and Andromeda passed a very long time ago. Gravity made the decision. The decision was made slowly, over billions of years of mutual approach, and there was never anything so dramatic as a point of no return, just the gradual accumulating certainty of two massive objects locked in a gravitational field that only gets stronger the closer they get. By the time the galactic disks are overlapping, by the time stars from two separate spiral galaxies are occupying the same volumes of space, the word collision is no longer a prediction. We are now approximately 4.5 billion years from the present. The first pass is underway. Let us be precise about what first pass means, because there is a tendency to imagine it as a single, catastrophic instant, a moment of impact followed by wreckage. That is not what is happening. The first pass is a process that takes somewhere between 500 million and 1 billion years from the moment the leading disk edges make contact to the moment the two galactic cores reach their closest approach and then separate again. Even at hundreds of kilometers per second of approach velocity, covering the tens of thousands of light years of separation between the two galactic centers takes an enormous amount of time. And during that entire traversal, the gravitational interaction between the two systems is ongoing, intensifying and transforming both galaxies simultaneously. Think of it less like two cars colliding and more like two enormous weather systems, hurricanes perhaps, or entire pressure fronts moving toward each other across a continent. The moment they make contact at their edges, the interaction begins, but the full drama, the peak wind speeds, the maximum pressure differentials, the most intense rainfall, comes as their centers approach and then pass through each other. The center-to-center closest approach. The moment when the two galactic cores are at their minimum separation during the first pass occurs approximately 4.5 to 4.8 billion years from now. In the models, this separation at closest approach is not zero. The two cores, The dense central bulges of stars surrounding each supermassive black hole will pass each other at a separation of perhaps 20,000 to 30,000 light-years. That is still an enormous distance by human standards. The separation between the Earth and the centre of the Milky Way is approximately 26,000 light-years. So the two galactic cores will fly past each other at roughly the distance that separates us from our own galactic centre. It is not a collision of the centres. Not yet. That comes later, after multiple passes, after billions of years of orbital decay through dynamical friction. The first pass is just that, a pass, a fly-through. The two galactic cores will approach, reach minimum separation, and then the galaxies will continue moving in their original directions, separate slightly, slow down due to gravitational drag, and eventually fall back together. But the pass itself is the most violent single episode in the entire merger story. What happens to the stars during the first pass is the result of a process that operates in three registers simultaneously: gravitational disruption of existing orbits, decompression of interstellar gas triggering star formation, and the ejection of stars into the intergalactic medium. Let us take each in turn. The gravitational disruption of stellar orbits is the most fundamental consequence of the collision. Every star in both galaxies has an orbit, a path through the galactic gravitational field that it has been following in some cases for billions of years. These orbits are stable under normal conditions because the gravitational field is smooth and symmetric and changes only slowly. During the first pass, the gravitational field experienced by any given star changes dramatically on a timescale of a few 100 million years, practically instantaneous in galactic terms. Stars in both galactic disks find themselves subject to gravitational forces that their original orbits never accounted for. On the systematic, ordered motion of a spiral galaxy, stars moving in roughly circular orbits around the galactic center, like the planets of a very large solar system, is disrupted. The orbital energy and angular momentum of individual stars is exchanged with the overall gravitational field of the merged system. Stars that were on stable circular orbits are now on highly eccentric elliptical paths, stretched orbits that carry them far from the galactic center before swinging back. Some stars gaining enough energy from the gravitational interaction are flung onto hyperbolic trajectories, paths that carry them entirely out of the merged system and into intergalactic space, never to return. These ejected stars, sometimes called hypervelocity stars, though the mechanism here is gravitational scattering rather than the black hole interactions that produce hypervelocity stars in our current era, will travel through intergalactic space for the rest of cosmic time, isolated, dark, no longer part of any galaxy. Lonely stars drifting through the void between galaxy clusters, burning through their fuel on timescales of billions to trillions of years, with nothing around them but vacuum and the faint cosmic microwave background. There is something in this that is worth sitting with. Individual stars, entire suns, some of them with their own solar systems intact, their own planets spinning in their own orbits, ejected from the merger entirely and sent into permanent exile in the dark between galaxies. The collision does not just rearrange stars within a galaxy, it throws some of them away, to permanently into a darkness from which there is no return. The gas compression and starburst is the second major process of the first pass, and it is, in many ways, the most spectacular. Both galaxies contain enormous reservoirs of interstellar gas, primarily hydrogen, the raw material from which all stars are made. In the Milky Way, this gas is concentrated in the spiral arms and distributed throughout the disk in clouds of various sizes, from small, dense molecular clouds a few light years across to vast diffuse regions spanning thousands of light years. Andromeda has a similar inventory, perhaps somewhat more gas than the Milky Way in some estimates. When the disks interpenetrate, the gas in both galaxies does something the stars do not do. It collides. Stars are point masses, or rather, they are so small relative to the distances between them that they essentially never collide during the galactic merger. But gas clouds are extended structures, and where gas clouds from the Milky Way and gas clouds from Andromeda occupy the same space at the same time, they interact physically. They compress each other. They shock each other. The astrophysical term for what happens when two streams of gas moving at different velocities collide, and the kinetic energy is rapidly converted into heat and turbulence. Gas shock fronts propagate through the interacting regions. The compressed, shocked gas achieves the critical densities needed for gravitational collapse. And star formation begins, not at the modest rate of a few solar masses per year that characterizes normal galaxies, but at a dramatically elevated rate that may reach hundreds of solar masses per year during the peak of the starburst. To put that in perspective, the current rate of star formation in the Milky Way is approximately 1 to 3 solar masses per year. During the peak starburst triggered by the Andromeda collision, the rate may be 50 to 100 times higher. In the most intense regions, the compressed gas lanes, the shocked interface between the two galactic disks, and particularly the region near the galactic centers where gas inflow will be greatest, new stars will be forming at a rate that would be essentially unrecognizable compared to anything our galaxy experiences today. The sky during this period will be full of the evidence of this explosion of star birth. Newly formed stars are hot. The most massive newly formed stars are extraordinarily hot, surface temperatures of 30,000 to 50,000 Kelvin compared to the Sun's 5,778 Kelvin. These stars radiate intensely in the ultraviolet, ionizing the gas clouds around them and causing them to glow in the characteristic pinks and reds of ionized hydrogen, the same colors seen in the Orion Nebula or the Eagle Nebula, but replicated across millions of star-forming regions simultaneously. If you could see in ultraviolet, the merging galaxies during the starburst peak would be almost blindingly bright. In visible light, the regions of active star formation will glow blue-white, studded with the brilliant pinpoints of young massive stars. These regions will be among the brightest features in the entire merging system, brighter, in some cases, than the galactic cores themselves. And they will be dying almost as fast as they form. Massive stars, the ones that form preferentially in starburst conditions because the compressed gas clouds tend to be large enough to produce high-mass collapse, live short lives. A star 20 times the mass of the Sun lives perhaps 8 million years. A star 40 times the mass of the Sun lives perhaps 4 million years. These are blinks of an eye in galactic time, and when they die as supernovae, explosions so energetic that they briefly outshine entire galaxies, releasing in their final seconds the energy equivalent of the Sun's entire 10 billion year lifetime. During the starburst peak, supernovae will be going off throughout both galactic disks at a rate that dwarfs anything in their current histories. Present-day rates in a galaxy like the Milky Way are approximately one supernova every 50 to 100 years. During the starburst, this rate might increase by a factor of 10 to 100. A supernova every few years, sometimes multiple per year, somewhere in the merging system. Each supernova is not just an explosion, it is a factory. The shockwave from a supernova blasts heavy elements, synthesized in the dying star's core, into the surrounding interstellar medium. Carbon, oxygen, neon, magnesium, silicon, sulfur, iron. The building blocks of rocky planets, the elements of biology. The collision is forging, in its violence, the raw materials for future worlds. Now, let us look at where the Sun is during all of this. Currently, the Sun orbits the galactic center at a radius of approximately 26,000 light-years. During the first pass, as we have already discussed, the Sun's orbit will be perturbed by the gravitational interaction of the merger. The question is, perturbed how much and in which direction? Computer simulations of the Milky Way Andromeda merger track the trajectories of test particles, stand-ins for individual solar systems, through the evolving gravitational field of the merging galaxies. These simulations show a wide range of possible outcomes for any given star's orbital history through the merger. Some simulations show the Sun being flung outward during the first pass, its orbit expanding to a larger galactic radius, carrying it into the outer regions of the merged system. Others show it being drawn inward toward the more densely populated central regions. In a small fraction of simulations, the Sun ends up in a tidal tail, a stream of displaced stars looping out away from the main body of the merged galaxy. The most important thing these simulations tell us is not where the Sun ends up, but how uncertain the outcome is. The merger is a chaotic gravitational event. Small differences in initial conditions lead to large differences in final outcomes. This is not a failure of the models. It is a genuine property of the physical system. The gravitational three-body problem is already chaotic for three objects. The Milky Way Andromeda merger involves hundreds of billions of objects. The trajectories of individual stars through the merger are, in a precise technical sense, unpredictable. What can be said is this: the Sun will almost certainly remain bound to the merged system. It will not be ejected into intergalactic space. It will continue to orbit within whatever structure the merged galaxy forms. But its orbital radius, its position within the galaxy, its stellar neighborhood, all of these may be dramatically different in the aftermath of the first pass. There is approximately a 12% chance, according to the most widely cited estimates, that the Sun will end up at a galactic radius more than twice its current distance from the center, flung outward into the sparse outer halo of the merged galaxy. There is a smaller but non-zero chance, at a few percent, that it will end up at a radius less than half its current distance, much closer to the chaotic central regions. For any civilization in the solar system during this period, and again, we should be honest about the extreme improbability of biological life as we know it persisting on this timescale, the most immediate consequence of the Sun's perturbed orbit would be a change in the night sky over geological time, as the solar system moves through regions of higher or lower stellar density, through regions of active star formation or quiet outer halo, through positions where the merging galactic cores are visible at different angles and separations. The sky would never be the same sky twice, not over millions of years. Let us talk about the galactic centers directly now, because during the first pass they are doing something that deserves its own careful attention. As the first pass reaches its closest approach, the moment when the two galactic cores are at minimum separation, the gravitational interaction between the two central bulges is intense. The central bulge of a galaxy is not like the outer disk. It is dense, tightly packed with old stars, most of them red giants and ancient main sequence stars that have been orbiting the galactic center for 10 billion years or more. The central bulge is the oldest, most stable part of the galaxy. When the core of Andromeda passes close to the core of the Milky Way, the gravitational tidal forces distort both bulges. Stars in the central regions are pulled and stretched. Some are flung into eccentric orbits. The smooth, roughly spherical structure of each bulge develops asymmetries, bars, loops, warps that would not exist in an undisturbed galaxy. More significantly, the passage of Andromeda's core near the Milky Way's center drives gas inflow toward Sagittarius, a star. Gas that had been in relatively stable orbits in the central kiloparsec, the central few thousand light-years, is disturbed by the tidal forces and begins falling inward. Sagittarius, a star currently quiescent at the dormant supermassive black hole at our galactic center, eating very little and producing relatively little radiation, may become significantly more active. There is a real, model-supported possibility that during the first pass, Sagittarius A star undergoes a period of elevated activity, perhaps not a full quasar, but a notably luminous, active galactic nucleus phase, and bright enough that an observer anywhere within a few thousand light-years of the galactic center would notice a dramatically brighter galactic core. Andromeda's central black hole, 110 million solar masses, compared to Sagittarius A star's 4 million, is even more likely to become active during this phase, as the encounter drives enormous quantities of gas toward its center. An active Andromeda nucleus, from the perspective of any star system within the merged galaxy's disk, would appear as an extremely bright point source at the center of the Andromeda component of the sky, a quasi-stellar source blazing at the heart of the approaching galaxy. Two active galactic nuclei in the same sky, separated by tens of thousands of light-years of apparent distance, but both visible, both blazing, during the peak of the first pass. It would be one of the most spectacular events any sky has ever hosted. After the closest approach of the first pass, something counterintuitive happens. The galaxies separate, not because the gravitational attraction between them has switched off or even weakened. It has not. Gravity never stops. But the galaxies have inertia. They arrived at the first pass with significant velocities, and those velocities carry them through and beyond minimum separation. In the same way that Earth, falling toward the Sun, under gravity, also has enough sideways velocity to perpetually miss, to curve into an orbit, rather than a collision, the galaxies have enough relative velocity after the first pass to continue moving apart for a time. But only for a time. After the first pass, the two galactic systems, both significantly distorted, are both trailing enormous tidal tails, both still lit with the fires of the starburst, move apart. The separation between the two cores increases. For a period of perhaps 1 to 2 billion years, the merger appears to pause. The most intense phase of the starburst subsides somewhat as the direct gas-gas collision in the overlapping disks ends. The tidal tails continue to evolve, stars continue to orbit on their new eccentric paths, but the dramatic closest approach is over. This interim phase, the period between the first and second pass, is not quiet. Both galaxies are profoundly changed. Neither looks anything like the clean spiral galaxies they were before. Their disks are warped and distorted. Their tidal tails stretch for hundreds of thousands of light years. Stars are scattered through the intergalactic medium in long streams and arcs. Yet the orderly spiral structure of both galaxies and the elegant pinwheel patterns of density waves and spiral arms that existed before the collision has been disrupted, but the two objects are still recognizable as distinct systems. Two merging but still separate galaxies bound together by gravity, now looping through a long gravitational arc that will bring them back together. The second pass will be more direct, more violent, closer. The second pass, the second closest approach of the two galactic cores, occurs perhaps 5.5 to 6 billion years from the present, roughly 1 to 1.5 billion years after the first pass. In the interim, the separation between the two cores reached perhaps 300,000 light-years at its post-first pass maximum before gravity reversed the separation and began pulling the systems back toward each other. By the time of the second pass, the galaxies are approaching each other again at significant velocity, but now both are more disrupted. Both have lost energy to the tidal interaction of the first pass, and the overall gravitational binding of the merged system is tighter. The second pass is closer than the first. The core separation at minimum approach is smaller, perhaps 10,000 to 15,000 light-years. This is a genuinely closer encounter of the two densest, most massive parts of both galaxies. The gravitational disruption is more severe. The tidal forces on the remaining disk structures are stronger. The gas inflow toward both galactic centers is greater. The second starburst is, in some ways, more intense than the first. This is a pattern seen in observations of other galaxy mergers. The antennae galaxies are in an early phase of interaction. Other merging galaxy pairs at different stages of their mergers show the double starburst pattern. The first triggered by the initial disk passage, the second, more intense burst, triggered by the second core approach. For the Milky Way Andromeda system, the second pass marks the beginning of the end of the distinct phase of the merger. After the second pass, the two galactic cores, though still separate, still carrying their distinct populations of central stars and their supermassive black holes, are much more tightly bound. The energy that would be needed to separate them completely is no longer available. The merger is, after the second pass, genuinely irreversible in any practical sense. Not that it was ever reversible after the first, but after the second pass. The endpoint is clear and close. The two cores will spiral inward and merge. Let us take a moment to talk about something that does not get discussed often enough in accounts of this collision: what happens to the Milky Way's satellite galaxies. We mentioned earlier that the Large Magellanic Cloud may collide with the Milky Way in its own separate event approximately 2 billion years from now, well before the Andromeda encounter. By the time of the first pass, the Magellanic Clouds, or rather their stellar remnants, after being absorbed by the Milky Way, will have been incorporated into the Milky Way's disk or halo. Andromeda's satellite galaxies, Messier 32, Messier 110, and the various smaller dwarfs in its retinue will be subject to the same tidal forces as Andromeda itself. The smaller, more loosely bound satellite galaxies will be stripped away early in the approach, their stars scattered into tidal streams in the region between the two main galaxies. The larger companions like M32 and M110 are more resistant, being more compact and more tightly bound. M32 in particular is unusual among Andromeda's satellites. It is a compact elliptical galaxy, one of the smallest and densest galaxies known, a tiny but extraordinarily dense stellar system that sits close to Andromeda's center. Current research suggests M32 may be the stripped remnant of a once much larger galaxy that was already partially consumed by Andromeda in the distant past. If this is correct, M32 is itself a survivor of a previous merger, and it will now be absorbed into the Milky Way Andromeda collision along with its parent galaxy. The local group. In the long aftermath of the Milky Way Andromeda merger, will be dominated by a single large galaxy, Milkomeda, surrounded by a much-reduced population of satellite dwarfs, the survivors of the pre-merger satellite systems of both major galaxies. Several of the current local group dwarfs will be absorbed. Others will persist as satellites of the new giant. A few may have been ejected during the merger, and now orbit the merged system at enormous distances or drift slowly toward or away from it in the manner of loosely bound companions. By the time the second pass is complete, roughly 6 billion years from now, the night sky as seen from the solar system, wherever it has drifted to in the merged system, is beyond any easy description. There are no clean spiral arms, no orderly disk. No easily distinguished our galaxy and their galaxy. The two systems have been so thoroughly mixed that any distinction between Milky Way star and Andromeda star is meaningful only in a historical sense, traceable in principle through stellar chemistry and orbital history, but not visible in any obvious way to an observer looking up at the sky. The sky is simply full. Fuller than it has ever been in the solar system's history. Stars in every direction, not as densely packed as in a globular cluster, not the blinding, brilliant sky of a star cluster's core, but richer, more complex, more layered than anything our current sky can offer. The background glow of the merged galaxy, the combined light of 2 trillion stars scattered through an irregular elliptical structure, is dimly present in every direction. There is no single clear band of the Milky Way anymore, arching cleanly overhead. There is instead a soft, diffuse luminosity that the sky carries as a background everywhere you look, with concentrations and voids, bright knots of star-forming regions, and the occasional brilliant blue-white cluster of young stars born in the starburst. And somewhere in that sky, somewhat separated, somewhat distinct, but visibly in the same sky, 2 bright concentrations of light, 2 galactic cores, each one a dense, luminous blaze of ancient stars, each one harbouring a supermassive black hole, each one the relic of what was once a clean, distinct, spiralling island universe. They are spiralling toward each other. The final act is beginning. There is a kind of ending that does not feel like an ending, not the sharp, decisive kind, not the door slamming shut, not the final note of a piece of music ringing out and then going silent, but the slow kind, the kind where the thing you knew and the thing it is becoming overlap for so long and so completely that there is no single moment you can point to and say, there. That was it. That was when it changed. Just the merger of the Milky Way and Andromeda is that kind of ending. By the time we reach the phase this part of our story covers, roughly 6 to 9 billion years from the present, both galaxies have already been through 2 close passes. Both have been distorted beyond recognition. Both are trailing enormous tidal structures into the surrounding void. The stars of one are already thoroughly intermixed with the stars of the other in the outer regions of the merged system. And yet the cores are still separate. Two dense concentrations of ancient stars, each surrounding a supermassive black hole, still orbiting each other within the body of the merged galaxy, separated by tens of thousands of light years, circling each other like two eyes in a face that is still deciding what expression to wear. The merger, technically, has been underway for billions of years. But the final act, the true, irreversible unification of the two galactic hearts, has not yet happened. This is the part where it happens. To understand how two galactic cores merge, we need to understand a force that sounds almost mundane given the scale of what it is doing. Dynamical friction. It is not one of the four fundamental forces. It is not gravity, or electromagnetism, or the strong or weak nuclear force. It is instead an emergent phenomenon, a consequence of gravity operating collectively across enormous numbers of objects, and it is the mechanism responsible for driving the two galactic cores of Milkomeda toward each other over billions of years. Here is how it works. When a massive object, say a dense galactic core containing billions of stars and a supermassive black hole, moves through a medium of other stars, it gravitationally attracts those stars toward it. The stars in front of it are pulled toward it and so decelerate in their approach. The stars behind it are also pulled toward it and so accelerate in its direction. The net result is a slight overdensity of stars trailing behind the moving object, a gravitational wake. This wake exerts a small but persistent gravitational pull backward on the massive object, opposing its direction of motion. It is, in effect, a drag force. The more massive the moving object, the stronger the wake. The denser the medium it moves through, the stronger the drag. For two galactic cores orbiting each other within the merged stellar body of Milkomeda, this drag force is continuously sapping orbital energy. Each orbit, the two cores lose a small amount of energy to dynamical friction. Each orbit, they fall slightly closer to each other. The orbital period gets shorter. The separation decreases. It is slow, it is relentless, and it will not stop until the two cores have merged into one. The timescale for this process, from the end of the second pass to the complete merger of the two galactic cores, is estimated at approximately 1 to 3 billion years. So, if the second pass occurs around 6 billion years from now, the core merger is likely complete by somewhere between 7 and 9 billion years from the present. As the two cores spiral inward, the galaxy they inhabit, the irregular, fire-scarred remnant of the first and second passes, is gradually settling. This settling is itself a fascinating process. The merger of two spiral galaxies does not simply produce a messy spiral. It produces an elliptical galaxy. This transformation from spiral to elliptical is one of the most important and well-documented processes in observational astronomy. We can see it happening at various stages in galaxy pairs throughout the observable universe. Spiral galaxies have a specific structural feature that makes them spirals, a thin, rotationally supported disk. The stars in a spiral galaxy's disk are all orbiting in roughly the same direction, in roughly the same plane, like the planets of an enormous solar system. It is this coordinated rotation that produces the flat disk shape and, through the action of density waves, the elegant spiral arm patterns. When two spiral galaxies merge, this coordinated rotation is disrupted. Stars from both galaxies end up on highly eccentric, inclined, randomly oriented orbits within the merged system. There is no longer a preferred plane of rotation. There is no longer a coherent disk. Instead, The merged system gradually relaxes into a pressure-supported structure, a system where the star's random motions in all directions provide the support against gravitational collapse, rather than organized rotation in a single plane. The result is an elliptical galaxy, a smooth, featureless, roughly spheroidal or mildly elongated distribution of stars, redder and older looking than a spiral, with no spiral arms, no disk, no prominent dust lanes, and no significant ongoing star formation. This is what Milkomeda will eventually become. Well, the transformation from two disrupted spirals to a settled elliptical takes time, perhaps 2 to 4 billion years after the core merger. During this relaxation phase, the irregular clumps and streams and asymmetries left by the collision gradually smooth out as stars undergo a process called violent relaxation. The rapid redistribution of stellar orbits in response to rapidly changing gravitational potentials. The merged galaxy slowly acquires the smooth, symmetric profile characteristic of ellipticals. But before that settled state is reached, there is one more extraordinary event to pass through: the black hole merger. At the center of the Milky Way sits Sagittarius, a star. 4 million solar masses, currently quiescent, the dormant giant at the heart of our galaxy. At the center of Andromeda sits its own supermassive black hole, approximately 110 million solar masses, roughly 27 times heavier. These two objects are, in terms of mass and gravitational influence, the most significant individual objects in the entire merger. As the two galactic cores spiral inward under dynamical friction, they bring their central black holes with them. For most of the inspiral, the billions of years of orbital decay, the two black holes are carried along passively, embedded in their respective stellar cores, orbiting each other at the same separation as the cores themselves. But at some point, when the two cores have come close enough that the orbital separation has shrunk to a few hundred light-years or perhaps a few tens of light-years, the dynamics change. At these small separations, the black holes themselves begin to dominate the gravitational interaction. The central few hundred light-years of the merged galaxy become a region where the combined gravity of the two black holes determines the orbital structure. Stars in this region are either ejected, flung out of the center by gravitational slingshot interactions with the binary black hole system, or captured and consumed. This phase, the binary supermassive black hole phase, is one of the most active areas of research in astrophysics. What happens when two supermassive black holes are separated by only a few light years, orbiting each other within a dense stellar environment? The answer is still being worked out, but the broad picture is becoming clearer. As the two black holes orbit each other at decreasing separations, or they interact with the surrounding stars through gravitational slingshot effects, three-body interactions in which a star passes close to the binary and receives a gravitational kick that accelerates it outward, while the binary loses a small amount of orbital energy. This process, called the loss cone mechanism, continues to drive the black holes together, though it is less efficient than dynamical friction was at larger separations. There is a theoretical problem called the final parsec problem. The question of whether this process stalls when the two black holes are separated by approximately 1 parsec, about 3.26 light-years, because at that point, the supply of stars on suitable orbits to interact with the binary runs low, and the remaining mechanism of energy loss becomes unclear. Current theoretical work suggests this problem is resolved, that in the messy, irregular, non-symmetric environment of a galaxy merger, there are always sufficient stars being scattered onto the necessary orbits to continue driving the inspiral. But the final parsec problem reminds us that the details of how two supermassive black holes actually complete their merger are still being understood. What we are more confident about is what happens when the separation shrinks below a parsec, below a few light years, and the two black holes enter the regime where general relativity becomes important. At sub-parsec separations, two orbiting black holes of these masses begin to emit gravitational waves. Gravitational waves are ripples in the fabric of space-time, oscillations in the curvature of space itself, propagating outward from accelerating massive objects at the speed of light. They were predicted by Einstein's general theory of relativity in 1916 and directly detected for the first time in 2015 by the LIGO detectors in the United States, which recorded the gravitational waves produced by the merger of two stellar mass black holes, each perhaps 30 solar masses, a billion light years away. The gravitational waves from stellar mass black hole mergers are high frequency, hundreds of oscillations per second, and detectable with kilometer-scale laser interferometers like LIGO. The gravitational waves from supermassive black hole mergers are something else entirely. The frequency of gravitational waves from an orbiting binary is set by the orbital period. Like two supermassive black holes, one of 4 million solar masses and one of 110 million solar masses, orbiting each other at sub-parsec separations, have orbital periods of years to decades. The gravitational waves they emit have periods of years to decades. These are not high-frequency waves detectable by ground-based interferometers. They are nanohertz frequency waves, oscillations so slow that they can only be detected by pulsar timing arrays, which use the ultra-precise ticks of millisecond pulsars distributed across the galaxy as a kind of cosmic detector grid. The energy carried away by these gravitational waves, even at the relatively low frequencies characteristic of this early stage, is significant. As the black holes radiate gravitational energy, their orbit shrinks. The orbital period decreases. The gravitational wave frequency increases. The power radiated increases. This is the beginning of a runaway process. A gravitational wave in spiral that operates on a timescale that goes from millions of years at large separations to thousands of years to days to hours to seconds as the separation shrinks and the gravitational wave emission becomes overwhelming. For the 4 million solar mass and 110 million solar mass black holes of the Milky Way and Andromeda, this gravitational wave inspiral will, over the course of millions to hundreds of millions of years, drive the two objects together until, in a final, catastrophic merger lasting perhaps a few years of real time, they collide and combine into a single, more massive black hole. The final moments of this inspiral, when the two event horizons are approaching each other, when the curvature of space-time in the immediate vicinity of the merging black holes is extreme enough to distort anything nearby beyond recognition, will release more energy in gravitational waves than the combined light output of every star in both galaxies over their entire lifetimes. In a few seconds, the gravitational wave burst from the merger of these two supermassive black holes will ripple outward through the universe at the speed of light, passing through the stars of Milkomeda, passing through the local group, passing outward across tens and hundreds and thousands of megaparsecs, a wave in space-time itself, carrying the announcement of the final unification of what were once two separate galaxies. It will not be dangerous. Gravitational waves, even from sources this powerful, they cause only tiny stretching and squeezing of space on the order of fractions of an atomic diameter across the entire span of a solar system. No planet will be disturbed, no orbit will be meaningfully changed, but it will be real. A measurable distortion in the fabric of space, detectable in principle from enormous distances, marking the moment when Milkomeda ceased to be two things and became one. Now let us attend to the question of the Sun and the question of Earth through this long phase of the merger. We should be honest again about what is and is not likely. The Sun is a G-type main sequence star. Its total lifespan on the main sequence, the hydrogen fusing phase, is approximately 10 billion years. It is currently 4.6 billion years old. It has, therefore, approximately 5 to 5.5 billion years of hydrogen fusion remaining before it exhausts its core hydrogen and begins the transition to a red giant. The first core passage of the Andromeda merger occurs at approximately 4.5 billion years from now, just at the edge of the Sun's remaining main sequence lifetime. By the time of the second pass, roughly 6 billion years from now, the Sun will have just exhausted its core hydrogen. By the time of the core merger, 7 to 9 billion years from now, the Sun will no longer exist as we know it. The Sun's final billion years of main sequence life will see it becoming progressively brighter, expanding very slightly, increasing in luminosity. At some point between 1 and 1.5 billion years from now, its luminosity will have increased sufficiently to push Earth's surface beyond the habitable zone. The oceans will begin to evaporate. The water vapor will accumulate in the upper atmosphere. The greenhouse effect will intensify, and Earth's surface will become too hot for liquid water. This is, for all intents and purposes, the end of Earth as a living world. Earth will not be destroyed. It will still exist as a rock orbiting the Sun for billions of years to come. But it will be a dry, hot, airless rock, something closer to Venus than to the world we know today. After the core hydrogen is exhausted, roughly 5 billion years from now, the Sun will begin to expand into a red giant. Over the course of a few 100 million years, it will swell to perhaps 200 times its current radius, and potentially engulfing Mercury and Venus and possibly Earth itself, depending on exactly how the mass loss and orbital expansion dynamics play out. The outer planets, Jupiter, Saturn, Uranus, Neptune, will survive, though significantly heated. The orbits of the outer planets may expand as the Sun loses mass through its stellar wind. By the time of the Andromeda collision's first pass, 4.5 billion years from now, the Sun will be either in the final stages of its red giant phase or beginning its transition to a white dwarf. The red giant phase ends with the ejection of the Sun's outer layers as a planetary nebula, a beautiful, expanding shell of ionized gas, illuminated by the hot stellar remnant at its center, and the collapse of the Sun's core into a white dwarf, a dense, Earth-sized object composed of carbon and oxygen, no longer fusing hydrogen, slowly cooling over billions of years. The solar system in the era of the Andromeda collision will be, in all likelihood, a white dwarf and its surviving outer planets. Earth, if it has not been engulfed during the red giant phase, will be a frozen, airless rock orbiting a cooling stellar cinder. No atmosphere, no oceans, no life. Just a dark, rocky world in orbit around a fading ember, carrying in its geology the compressed record of 4.5 billion years of a living world, the fossils of creatures that once swam and walked and thought and wondered, now preserved in stone through the deep time of the universe's middle age. And that solar system, the white dwarf, the dead worlds, the surviving outer planets, will drift through the merger of two galaxies. Its orbital trajectory will be perturbed. Its galactic neighborhood will change, but the solar system itself, the orbits of the surviving worlds around their stellar remnant, will in all likelihood persist. The solar system is extraordinarily robust. It has survived 4.6 billion years of impacts, radiation, solar variability, and gravitational perturbation. It will survive the galactic merger. It will just be unrecognizable from what it was when it started. In the interval between the second pass and the core merger, roughly 6 to 8 billion years from now, the merged galaxy is settling into its new form. The starburst has peaked and is fading. The most massive stars born in the collision have already lived their entire lives and exploded as supernovae. When the interstellar gas that fueled the starburst has been either converted into stars or expelled from the galaxy by the combined energy of the supernovae and any active galactic nucleus activity. The gas reservoir of Milkomeda, the raw material for new star formation, has been substantially depleted. Elliptical galaxies are, broadly speaking, red and dead. Their star formation has largely ceased. They are dominated by the light of old, red stars, and they lack the blue-white brilliance of active star-forming regions. As Milkomeda settles into its elliptical form, it will transition from the violent, gas-rich, actively star-forming chaos of the merger to the quiet, ancient, slowly cooling character of an old elliptical. This is not death, it is age. And the stars that have already formed, the hundreds of billions of stars from both the Milky Way and Andromeda, plus the additional billions born during the starburst, will continue to burn for billions to trillions of years. The most massive stars are long gone, dead in the starburst that accompanied the collision. But the vast majority of stars are lower mass, sun-like stars, orange dwarfs, red dwarfs, with lifetimes measured in tens of billions to trillions of years. Milkomeda, in its settled elliptical form, will be a vast, quiet city of ancient stars. Trillions of solar systems, most of them old, rocky planets that formed billions of years ago, orbiting stars that have been burning for just as long. Some of those stars will still be on the main sequence. Some will have evolved into giants and white dwarfs, and among them, mixed in from the original populations of both galaxies and born in the starburst, will be new generations of stars, younger suns, perhaps with their own newly formed rocky planets, seeded with the heavy elements expelled in the collision's supernovae. The merger does not just destroy, it also creates the conditions for new beginnings. There is one final feature of the merger phase that is worth examining before we move to the full picture of what Milkomeda will look like in its settled state. The fate of globular clusters. Both the Milky Way and Andromeda have extensive populations of globular clusters, dense, spherical collections of tens of thousands to millions of stars, gravitationally bound into compact objects that orbit the main body of each galaxy in the extended halo. The Milky Way has approximately 150 to 160 known globular clusters. Andromeda has a richer system, several hundred, including some unusually massive examples. During the merger, the globular clusters of both galaxies will be scattered by the tidal forces of the collision. Some will be disrupted, torn apart by gravitational tides, and their stars scattered into stellar streams throughout the merged galaxy. Others, particularly the most compact and most massive, will survive the merger intact. They will become the globular cluster population of Milkomeda, a rich system drawn from the combined populations of both parent galaxies. Globular clusters are ancient, most formed in the very early universe within the first few billion years after the Big Bang, when the universe was denser and conditions were favorable for the formation of these dense stellar aggregates. They are, in a sense, survivors, objects that have persisted for 10 billion years already through the formation and evolution of their host galaxies, through earlier mergers and interactions, through the slow attrition of stars lost to the galactic tidal field. They will survive Milkomeda's formation, and in the deep future, long after the last gas cloud has been converted into stars or expelled, long after active star formation has ceased entirely, long after the galactic disk has settled into its final elliptical shape, the globular clusters of Milkomeda will still be there, orbiting the merged galaxy's center in long, slow ellipses, carrying within them the oldest stars in the universe, the ancient, even by the standards of a 10-billion-year-old galaxy. It is approximately 8 to 9 billion years from now. The core merger is complete, or nearly so. The supermassive black holes have spiraled together and merged. A new black hole of approximately 114 million solar masses now sits at the center of Milkomeda, the product of two separate cosmic histories fusing into one. The black hole merger's gravitational wave burst has long since radiated outward across the universe. The tidal tails from the original collision, those vast rivers of stars drawn out in the first and second passes, are still present. Tidal tails are remarkably persistent structures. Even billions of years after a galaxy merger is complete, the tidal tails of the progenitor galaxies can still be detected as faint stellar streams in the outer halo of the merged system. They will gradually dissolve, their stars slowly dispersed by the galactic gravitational field, but they will persist for a very long time, ghostly relics of the two separate spiral galaxies that once flew through each other in the middle age of the universe. The merged galaxy, Milkomeda, occupies a volume roughly comparable to a large elliptical galaxy. Its stellar mass is the sum of the Milky Way and Andromeda's stellar masses, plus whatever was added in the starburst, somewhere in the range of 1.5 to 2 trillion solar masses in stars. Its central black hole at 114 million solar masses is large but not extreme by the standards of massive elliptical galaxies. Those can reach billions of solar masses. Milkomeda's light is dominated by old stars, the integrated glow of hundreds of billions of ancient suns, most of them orange and red. Its color, compared to the blue-white of an actively star-forming spiral, is warm and yellowish-red. It is the color of age, and it is, at last, one thing instead of two. Somewhere in its outer regions, in some orbit that has drifted far from where it started, a white dwarf is orbiting the center of Milkomeda. It has been orbiting for billions of years. It is the collapsed remnant of a yellow star that once burned in the outer disk of a galaxy called the Milky Way, warming a rocky world with liquid oceans and an oxygen atmosphere, illuminating a blue sky above creatures that looked up and once saw a faint smudge in the night and wondered what it was. The wondering is long over. The sky above any world in Milkomeda no longer contains that faint smudge. There is no Andromeda to wonder at. There is no Milky Way to arch overhead. There is only Milkomeda, The merged galaxy, the settled elliptical, the quiet city of ancient stars that these two galaxies became when they finally ran out of room between them. But the story is not quite over. There is a particular kind of silence that comes after something enormous has finished. Not the silence before, which carries tension, anticipation, the held breath of something about to happen, but the silence after, when the event that defined everything for so long has finally run its course, and what remains is the aftermath, the settling, the long, quiet consequence of forces that have spent themselves completely. The universe in the era we are entering now has that quality. We have followed the clock from the present day, from a faint smudge in the night sky 2.537 million light-years away, through the long approach, through first contact, through the violence of the first and second passes, through the slow spiral of two galactic cores finding each other in the chaos and merging into one. We have watched two separate galaxies, each containing hundreds of billions of stars, each with its own history and structure and identity, become a single thing. That single thing, Milkomeda, is now the subject of this final chapter. But Milkomeda is not the end of the story. It is barely the beginning of the end. Because the universe in which Milkomeda exists is still young, even at 9 billion years from now. The universe is currently approximately 13.8 billion years old. 9 billion years from now, it will be approximately 23 billion years old. In cosmic terms, it will be entering what some cosmologists call middle age. The era of stars, the long epoch during which nuclear fusion powers the universe's light, is still very much ongoing. The real ending is much further away, and to understand it, we need to follow Milkomeda, not just for a few billion years, but for trillions. Let us establish where we are. Approximately 9 billion years from now, the universe is 23 billion years old. Milkomeda has completed its merger. The two galactic cores have united, the central black hole of the merged galaxy has settled, and the irregular tidal remnants of the collision are slowly smoothing into the featureless, elliptical profile of the final galaxy. Milkomeda is large. It is one of the dominant galaxies of what was once the local group, the family of more than 50 galaxies to which both the Milky Way and Andromeda once belonged. But the local group itself has been changing. Over the billions of years that the Milky Way-Andromeda merger has been unfolding, the other members of the local group have been evolving too. The smaller galaxies, the dwarf irregulars, the dwarf spheroidals, the satellite galaxies of both major players have been subject to the same gravitational forces. Some have already been consumed, incorporated into either the Milky Way or Andromeda over the course of their long histories. Others will eventually be consumed by Milkomeda. The Triangulum Galaxy, Messier 33, the third largest galaxy in the local group, a modest spiral about half the size of the Milky Way, currently approximately 2.7 million light-years away, is also gravitationally bound to the local group. Simulations of the local group's future suggest that M33 may merge with the Milky Way-Andromeda system, either during the main collision or in a subsequent encounter, becoming part of Milkomeda itself. The timing is uncertain. It may arrive before the Andromeda first pass, during the merger, or afterward. But on the timescale of tens of billions of years, it will almost certainly become part of the merged system. The smaller dwarf galaxies of the local group, objects like the Sculptor dwarf, the Fornax dwarf, the Carina and Sextans, and Draco and Ursa, minor dwarfs, and dozens of others will either be gradually absorbed by Milkomeda's gravitational pull, disrupted into stellar streams, or, in a few cases, ejected into the expanding cosmic web. This process, the consolidation of the local group into a single massive object, will be largely complete within approximately 150 billion years from the present. By that point, Milkomeda will have consumed essentially all of the local group's mass that is gravitationally bound to it, becoming a single enormous elliptical galaxy surrounded by a scattering of widely dispersed stellar streams and the orbiting remnants of the last dwarf satellites. But there is something else happening on this timescale that dwarfs even the local group's consolidation. The universe is expanding. It has been expanding since the Big Bang, and it is not merely expanding, it is accelerating. The expansion of the universe is speeding up, driven by a form of energy embedded in the fabric of space itself, which physicists call dark energy. Dark energy acts like a repulsive force on cosmic scales, pushing the large-scale structure of the universe apart at an ever-increasing rate. On small scales, the scale of galaxies, of the local group, of galaxy clusters, gravity wins. Objects that are gravitationally bound to each other remain bound, regardless of the cosmic expansion. The Milky Way and Andromeda are falling toward each other precisely because their mutual gravity is stronger than the cosmological expansion pushing them apart. But on large scales, the scale of the distances between galaxy clusters, and especially at the distances between the superclusters of galaxies, dark energy wins. Distant galaxy clusters are already receding from us faster than light, and as the universe continues to expand and accelerate, more and more of the observable universe will recede beyond what cosmologists call the cosmic horizon, the distance beyond which the expansion of space carries objects away from us permanently, and light from those objects can never reach us. At the current rate of expansion, any galaxy not already gravitationally bound to the local group, any galaxy that is merely in our cosmic neighborhood, but not our gravitational family, will eventually recede beyond our horizon. Its light will redshift into longer and longer wavelengths, growing dimmer and dimmer until it disappears entirely, not destroyed, just unreachable, separated from us by an ever-widening gulf of expanding space. The universe is, in a very real sense, slowly evaporating our observable neighborhood. In approximately 100 billion years, essentially all galaxies outside our local group will have receded beyond the cosmic horizon. From within Milkomeda, looking out into the universe, the sky will appear empty of other galaxies. The rich, structured cosmic web, the network of galaxy filaments and voids that defines the large-scale structure of the present universe, will be gone from view. The universe will appear from inside Milkomeda to consist of a single large galaxy, surrounded by an infinite, dark, and featureless void. It will be profoundly lonely if loneliness can apply to a galaxy. All the evidence of the universe's larger structure, the other galaxy clusters, the great walls of galaxies, the cosmic filaments, will have vanished beyond the horizon. Any civilization that arose within Milkomeda in that era and looked out at the sky would see no other galaxies. They would have no direct evidence that other galaxies ever existed. The entire observable universe from their perspective would be Milkomeda and nothing else. The era of stars, what Fred Adams and Greg Laughlin called the stelliferous era, in their foundational work on the deep future of the cosmos, will continue for an extraordinarily long time. after Milkomeda's formation. The most massive stars, the blue supergiants and bright O-type stars, have lifetimes of only a few million years. They are already gone, dead in the starburst of the merger and in the ordinary star formation of the preceding billions of years. Sun-like stars, G-type main sequence stars, have lifetimes of approximately 10 billion years. Many of them were formed in the early universe 10 or 12 billion years before the present, and are already gone. Others formed more recently and will continue to burn for several billion years. But within approximately 5 to 10 billion years after Milkomeda's formation, so perhaps 15 to 20 billion years from the present, most Sun-like stars will have exhausted their hydrogen and transitioned to white dwarfs. The stars that will live longest are the red dwarfs, the M-type main sequence stars that are far smaller, cooler, and more fuel-efficient than the Sun. A red dwarf with a mass of 0.1 solar masses burns its hydrogen so slowly that it can remain on the main sequence for approximately 10 trillion years, roughly 1,000 times the current age of the universe. These stars are the long-lived embers of the stellar era, the last to fade. In Milkomeda, the stellar population will evolve slowly over the coming trillions of years. The hot stars will be long gone. What remains will be a galaxy increasingly dominated by small, dim red stars, M-type dwarfs, glowing a deep crimson, each one burning so slowly that it would be almost unrecognizable as a star to anyone accustomed to the sun's brilliance. But burning, nonetheless, still producing light, still potentially warming worlds. If any planets orbit these long-lived red dwarfs, and red dwarfs do indeed have planets, we know this from modern observations, then those worlds might remain in some form of habitable condition for unimaginably long time scales. Not the 4 billion year window that Earth has had, but 10 trillion years, 100 trillion years. The collision of the Milky Way and Andromeda, twice, triggering a starburst that created billions of new stars, including many new red dwarfs, may have extended the window of stellar warmth in this region of the universe by trillions of years, beyond what would otherwise have been the case. Approximately 100 trillion years from the present. The last red dwarf in Milkomeda is burning out. The precise timing is uncertain. It depends on the initial mass function of the stars formed in the merger and in the subsequent quiet star-forming episodes of the early merged galaxy, and on the exact mass of the last and least massive red dwarfs. But somewhere in the range of 1 to 100 trillion years from now, the last nuclear fires in Milkomeda will go out. This moment, the death of the last star, is the end of the stelliferous era. It is, in some ways, the most significant threshold in the entire future history of the universe. The cosmos has been a place of light since the first stars ignited approximately 200 million years after the Big Bang. For all the time since, for the entire age of the universe to date, and for trillions of years beyond, light has been available. Warmth has been available. The energy gradient necessary for complex chemistry, for life, for thought, has been available somewhere. After the last star dies, the universe enters what Adams and Laughlin call the degenerate era. Milkomeda, at this point, is no longer a galaxy in the conventional sense. Its stars are not stars anymore. They are stellar remnants, white dwarfs, neutron stars and black holes, the white dwarfs, once the bright remnants of sun-like stars, are now cooling slowly. They have been cooling for trillions of years. The hottest of them have long since faded through white to yellow to orange to red and are now barely glowing. Objects sometimes called black dwarfs, though this term is theoretical because the universe has not yet been old enough for any white dwarf to cool completely. In the degenerate era, the universe is dark. Not perfectly dark. The cooling white dwarfs still emit faint infrared radiation. Very occasionally, two white dwarfs orbiting each other in a binary system will spiral together and merge, triggering a Type 1a supernova, a brief, brilliant flash of light that illuminates the dark galaxy for a few weeks before fading. These flashes become progressively rarer as the white dwarf population is consumed, but they are among the last significant light-producing events in the universe. That the central black hole of Milkomeda, the 114 million solar mass object that was once Sagittarius A star, and Andromeda's central black hole, now merged, sits at the center of the dark galaxy. Around it, the remnants of trillions of solar systems orbit in silence. There is one more process happening during the degenerate era that will, on long enough timescales, consume even the stellar remnants: gravitational evaporation. A galaxy is a gravitationally bound system, but it is not perfectly bound. Stars, or in the degenerate era, the stellar remnants that have replaced them, interact with each other gravitationally over time. In a process called relaxation, these gravitational interactions gradually redistribute energy among the objects in the galaxy. Some objects gain energy, others lose it. Objects that gain enough energy are eventually moving fast enough to escape the galaxy entirely. They are evaporated out of the system. Objects that lose energy fall inward toward the center, toward the central black hole. This process operates on an extraordinary timescale. For a galaxy like Milkomeda, the relaxation time, the timescale on which gravitational evaporation significantly depopulates the galaxy, is approximately 10 to the power of 19 years. That is 10 quintillion years. 10 quintillion years. This is so far beyond any timescale we have discussed that it requires its own moment of reckoning. The current age of the universe is approximately 13.8 billion years. 10 quintillion years is roughly 700 million times the current age of the universe. On this timescale, Milkomeda dissolves, not in an explosion. Not dramatically, but grain by grain, stellar remnant by stellar remnant, object by object, evaporated away by the slow statistical process of gravitational interactions, gradually speeding up some objects until they escape, while the remainder fall inward. What is left, after most of the stellar remnants have either been evaporated into the void or consumed by the central black hole, is the black hole itself. The central black hole of Milkomeda, 114 million solar masses at the time of the merger, but grown considerably larger by billions of years of consuming infalling stars and gas and stellar remnants, will be the last significant object in what was once one of the most complex gravitational systems in the local group. But even black holes do not last forever. Stephen Hawking demonstrated theoretically in 1974 that black holes emit radiation, now called Hawking radiation, as a consequence of quantum effects near the event horizon. The black hole slowly loses mass through this radiation. It evaporates slowly, almost impossibly slowly. The black hole shrinks. The timescale for Hawking evaporation depends enormously on the mass of the black hole. For a stellar mass black hole, the evaporation time is already longer than the current age of the universe by an enormous factor. For a supermassive black hole of 114 million solar masses, the Hawking evaporation time is approximately 10 to the power of 97 years. This number is so large that it does not meaningfully compare to anything else in this script. It is larger than the number of atoms in the observable universe. It is larger than any other timescale we have discussed by a margin so vast that the gap between now and the death of the last star, itself a span of trillions of years, is completely invisible by comparison. But it is finite. Eventually, after a span of time so long that every other event in this entire story, from the first faint blue shift of Andromeda's light, to the merger of the galactic cores, to the death of the last red dwarf, occupies only the tiniest sliver at the very beginning. The black hole at the center of Milkomeda will complete its evaporation. In its final moments, as its mass drops below a certain threshold and its temperature spikes and the Hawking radiation intensifies into a brief burst of high-energy particles, the last significant remnant of the Milky Way and Andromeda merger will release a small flash of radiation. And then, nothing. The space that was once Milkomeda, that was once the Milky Way and Andromeda, that was once two spiral galaxies, each containing hundreds of billions of stars, each orbited by millions of planets, each perhaps seeding the universe with the conditions for life and thought and wonder, will contain nothing but the slowly dispersed stellar remnants that escaped through gravitational evaporation, themselves cooling and fading over their own extraordinary lifespans, orbiting in the dark and empty void, long past any possibility of interaction. Let us come back. Let us come back to the beginning of the story, because the ending is only meaningful in the context of what came before. Right now, tonight, as you lie in the dark, Andromeda is 2.537 million light-years away. The light entering your eyes when you look at it left that galaxy when the genus Homo was just beginning to walk upright on the African savanna. The photons that carry your view of Andromeda have been travelling through intergalactic space for longer than our species has existed, and in the time it takes those photons to complete their journey, Andromeda closes approximately 110 kilometers of the distance between us, 110 kilometers per second. The two galaxies have been closing this gap for longer than the Earth has existed. They will continue closing it for longer than the Earth has left to live. The deadline, 4.5 billion years, is both incomprehensibly far away and already, in a cosmic sense, almost upon us. The universe is 13.8 billion years old. The collision happens at roughly 18 billion years. We are already 2/3 of the way to the deadline on the universal clock. The thing about this collision, the thing that separates it from most of the catastrophes and countdowns in the universe's history, is that it is not a sudden event. It is not an asteroid impact, over in seconds. It is not a supernova, over in hours. It is not even the death of a star, which at least completes itself within a human meaningful span of time relative to the universe's age. The Andromeda collision is a process that will last billions of years. It will begin while life on Earth still exists, or rather, while the solar system is still in roughly its current form. It will complete long after the solar system has been transformed beyond recognition. It spans a duration longer than the entire age of the Earth, more than 4 times over, and it is already underway. The gravitational field of Andromeda is already pulling on the Milky Way. Already, the trajectory of every star in our galaxy is influenced at some infinitesimal level by the mass of that approaching galaxy. The two systems are already locked in the embrace that will eventually consume them both and produce something new. What does it mean? This is the question that has been implicit in every sentence of this story. The question that makes this more than an astronomy lecture. The question that makes it feel personal. Even though the collision will happen long after any human alive today, long after any descendant of any human alive today, long after any biological life on Earth of any kind is gone. What does it mean that the sky above us contains, in plain view on a clear night, the galaxy that will collide with ours? One answer is that it means nothing at all in any immediate or personal sense. It is a fact about the universe, like the fact that the universe is 93 billion light-years across, or that the nearest star is 4.24 light-years away. True, staggering in its scale, but not something that changes how you live your Tuesday. But another answer, the answer that keeps drawing people back to these stories, and that makes sleeplessness lie awake thinking about them rather than drifting off the way they planned, is that it means something about scale, about the scale of what exists and the scale of what we are within it. We live on a rocky world orbiting an ordinary star in the outer disk of a spiral galaxy. We have existed as a species for perhaps 300,000 years. We have had writing for perhaps 5,000 years. We have understood in any scientific sense what Andromeda is, not a cloud of gas, not a nearby nebula, but an entire galaxy 2.5 million light-years away for barely 100 years. Edwin Hubble established this in the 1920s. 100 years ago, we did not know what Andromeda was. Now we know not just what it is, but where it is going. We know its velocity. We know its trajectory. We have simulated, with billions of test particles running on supercomputers, the detailed gravitational choreography of the next 10 billion years of its interaction with our galaxy. We know what the night sky will look like in 4 billion years. We know that the two galactic cores will spiral together and merge. We know that the merged system will settle into an elliptical galaxy. We know that the last stars will die. We know the time scale of the black hole's evaporation. We know this. We, creatures whose entire written history fits inside a margin of error in these calculations, creatures who discovered that galaxies were galaxies barely a century ago, have worked out the trajectory of the universe in this corner of space for the next 10 to the power of 97 years. There is something extraordinary in that. A makrim, something that is easy to miss when the numbers get large enough to become abstract. The collision is also, in a very real sense, a story about identity. The Milky Way and Andromeda will merge. Milkomeda will form. And within Milkomeda, every star that was once in the Milky Way and every star that was once in Andromeda will continue to exist. The same stars, the same hydrogen-fusing cores, the same nuclear fires, but they will no longer belong to separate galaxies. The distinction between Milky Way star and Andromeda star will persist only in the chemical fingerprints of individual suns, in the detailed orbital histories that could, in principle, be traced back to show which galaxy a given star came from, but not in any observationally obvious way. Are they the same galaxies? Are they something new? The answer is both. The merger does not erase what came before, it transforms it. The individual stars persist. The individual solar systems, if they survive, persist. The laws of physics that govern them remain unchanged, but the structure that held them together, The galactic identity, the coordinated rotation of a disk, the spiral arms, the distinct core that is gone. What exists is new, a new structure built from old materials in a new configuration. This is perhaps as close as astrophysics gets to a meditation on impermanence. Everything changes, slowly, on timescales that dwarf all human experience, but inexorably and completely. The Milky Way we think of as permanent, the arch of light overhead on a clear night, as familiar and eternal seeming as the sky itself, is not permanent. It has a shape that will be unrecognizable in 5 billion years. It has a neighbor that will consume it. It has a clock attached to it, and the clock is running. And all of this, the approach, the first contact, the passes, the starburst, the core merger, the settling elliptical, the cooling stars, the final black hole, the last evaporation, all of it is visible in a sense right now. The faint smudge in the sky above Cassiopeia is the entire future of our galaxy, carrying its arrival time in the Doppler shift of its light, bluer than it should be, coming closer. One last image, imagine in approximately 4 billion years, a world. We do not know what kind of world. Perhaps it orbits a red dwarf, a long-lived star, stable and cool, formed in the starburst of the early merger. Perhaps it formed from the enriched interstellar gas of the collision, seeded with heavy elements forged in the supernovae of massive stars. Perhaps it has water. Perhaps it has an atmosphere. Perhaps, in the improbable but never impossible way of the universe, it has life. On this world, on a night with no moon, a creature, whatever kind of creature it might be, looks up. And the sky is full. Not the sky we know, not the single arch of the Milky Way, the handful of bright stars, the faint smudge of Andromeda. This sky is dominated by the merged galaxy, the combined light of nearly 2 trillion stars spread across the dome of the sky in a vast, complex, multi-layered structure. Bright knots where the starburst is still producing young blue-white stars, dark lanes of dust, the warm glow of billions of ancient red stars. And somewhere, in the center of it all, the faint, luminous concentration of the merged galactic core, the resting place of the black hole that was once 2 black holes in 2 galaxies that once were separate. The creature looks up and sees all of it without knowing what it is looking at. It does not know that the light above it comes from 2 galaxies that were once separate. It does not know about the 4.5 billion year countdown that preceded it. It does not know about the faint blue shifted smudge that a short-lived species on a small rocky world once noticed in the night sky and spent a century trying to understand. But the light is still there. The light from 100 years of human astronomy, the spectra taken at Lowell Observatory, the Hubble observations, the Gaia measurements, the supercomputer simulations did not cause the collision. They just described it. The collision was always going to happen. Andromeda was always going to arrive. The clock was always running. We were just the species that was here long enough and curious enough and able enough to read the clock, to know that it was coming, to lie in the dark and think in 4.5 billion years the sky changes forever, and to find in that knowledge, not terror exactly, but something richer and stranger than terror, something like perspective, something like the feeling of being very small in a very large universe and knowing it, and finding that knowing it is not diminishing, but expanding, that the mind that can hold a 10 to the 97-year time scale, even briefly, even imperfectly, has done something that nothing else in the visible universe is known to do. The galaxies collide because gravity compels them to. We understand the collision because curiosity compels us to. And in the end, in the dark, with Andromeda rising quietly over the horizon, the most distant object visible to the naked eye, the far shore of our cosmic neighborhood, the galaxy that is falling toward us at 110 kilometers per second as you listen to this, that might be the most extraordinary thing about the whole long story. Not that it is coming, but that we know.